Hey guys, and welcome back, and this week's video is going to be about electron configuration. More specifically, this is what you have to know as the electron configuration for the IB syllabus, but it's also present in other syllabuses, and just for your interest, I'm just specifying so you know what you are learning. So let's take a quick look at what we knew before. Before we had the nucleus is the little dot, and the energy levels, we had 2 electrons in the first, 1, 2, 3, 4, 5, 6, 7, 8 in the second, 1, 2, 3, 4, 5, 6, 7, 8 in the third, and we would come out to something like 2, 8, 8, and then some other electrons would have something like, some other atoms would have something like 2, 8, 7, 2, 4, whatever. This is false. It's not false, let's be clear. It's oversimplified. But now we're going to go a little bit deeper. So in reality, we have our main energy levels. We sometimes represent them as N. And main energy levels can be like the first main energy level, the second, the third, the fourth, etc. And this is exactly what we have seen over here. So this would be our first energy level, second, third, but now we go a bit deeper than that. So within our main energy level, we have subshells. In fact, sometimes energy levels are referred to energy shells, thus the subshells, and there are different subshells. We have the S subshell, the P subshell, the D subshell, and the F subshell. And what you also have to know is that not every single energy level has every single subshell, but it's quite easy to remember and understand because it goes in ascending order. The first energy level has only the first energy subshell, S. The second has 2S, and it has also the P subshell. Now the third, and by the way, I'm writing this as to indicate that we have the first main energy level, the second, or whatever. The third has the S, has the P, has the D, does not have the F, we're just adding the D here. And the fourth has S, P, D, and F. And then if you go further, we kind of stop at F because there's no really atoms that can go further than that, but they're also hypothetical orbitals, but you do not have to know that. This is where it stops for us. Now, to make matters a bit even more in detail, each subshell has different orbitals. So the S subshell, it has only one orbital, it's a sphere, and there's only one possibility. The P subshell, on the other hand, has 3 orbitals. It has one that goes like this. It looks a bit more symmetrical, but I'm sorry. We'll see a diagram just in a second. It has one subshell here, one here, and then another one over here. So it has 3 orbitals. The D, I'm not going to draw it. It has 5 orbitals. And the F has 7 orbitals. Now, what else we should know is that this is quite important to remember, that you have 2 electrons per orbital. So what does this mean? If we have S and it only has 1 orbital, then we can only have 2 electrons in the S shell. If we have P and we have 3 orbitals, we can have 6 electrons because 1, 2, 3, 4, 5, 6. Then we have D, so we can have 10 electrons, and F, we can have 14 electrons. So just to sum up what we've been doing over here, so within our real electron configuration, we have the main energy level, which has different subshells, and those different subshells have different orbitals that can fit different numbers of electrons in it. So just a quick look at the notation before we move on. So when we write electron configuration, you will be seeing a lot of this notation. This number in front is the main energy level. This is the subshell. And this is the number of electrons in that subshell. In this case, it's full and there's 2 electrons. So this is, let's just take a look at the diagram where you might see it a bit better than what I have drawn. You have the S shell, which is a sphere, 2 electrons in here. You have the P shell, 2 electrons per orbital, 1 orbital, 2 orbital, 3 orbitals, so you have 6 electron total. And in the D subshell, this diagram doesn't feature. I don't know why, but I took it because it was licensed, so I could use it for this video. But basically, there's another orbital possibility right here. So you have two electrons here, 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons somewhere here, and you're going to have 10 electrons total. So let's visualize this, because like, what do you mean orbitals? Do they go like next to each other? They go on top of each other? Like what? Exactly. So let's start off with, there's a nucleus where the axes intersect. Then we have the 1s shell. Okay, and this is where it ends. Then as you move on, your shells get bigger in the sense of bigger in energy. So then you're going to have your 2s shell, and then you're going to have your 2p shell, or 2p subshell, sorry. And then you're going to have your 3s, and then you're going to have your 3p, and etc. So this might look a bit confusing, but I hope it kind of helped you visualize how these orbitals come to existence in real life and what you can visualize them as, if it's too abstract, because we're looking at them separately over here, but when we put it all together, this is kind of what our atom would look like. Now, where this might get confusing is over here. So we can see as higher energy levels, we're making a smaller jump each time. So energy levels converge. And this is why I stopped at the 3p shell. Not because I didn't want to draw it, although it will look confusing, but because we would not draw the 3d shell next, we would draw the 4p shell next, which is what we can see over here. So 1s is lower than 2s, lower than 2p, and this comes from the fact that 1 is less than 2, is less than 3, is less than 4 in the main energy levels, and the s is less energetic than p, is less energetic than d, is less energetic than f. But when you put them together, you see that 4s is actually less energetic than 3d, or 5s is less energetic than 4d. So we fill up 4s before we fill up 3d. So let's take a quick look at how to remember that. So let's write, and what I suggest to do is you write out your electron configuration for all of these different main energy levels. You have 1s2, you have 2s2, you have 2p6, you have 3s2, you have 3p6, you have 3d10, and you have 4s2, you have 4p6, 4d10, and 4f14. And for example, 5s2, 5p6, 5d10, and 5f14, etc. And now, in order to know what order to fill it out in, you draw diagonal arrows. So you go 1s2, you go 2s2, 2p6, 3s2, and this is all so far nice. You go 1s2, 2s2, 2p6, 3s2, this all in order. But here you have 3p6, and then you move on to s2, not 3d10. Only after filling up s2 do you go to fill up 3d10, and then you fill up 4p6 and then 5s2. So this is already getting quite confusing, but usually let's just stick to the anomaly that is most common, which is the fact that 3d10 is more energetic than 4s2, thus we fill it up first. Fill 4s2 up first. So this goes back to a couple of rules that I have been meaning to mention. In fact, that we start at n equals 1, and then we go from there. So we go from n equals 1 to n equals 2 to etc. Also, electrons fill orbitals or subshells in ascending energy levels. So you go from highest to lowest. So this is why we have 4s2 before 3d10. Because electrons will fill up the lowest energy first and then move on to the highest energy. And lastly, let's go back to the rule of 2 electrons per orbital, which is where all of these numbers come from. There's a couple more rules, but those can be mentioned in another video, and it's the Aufbau principle, but today we'll just focus on really the basics, and this is where we're moving on with our examples. So let's try to configure calcium. Calcium has the atomic number of 20, so it has 20 electrons. So we're going to start off with, again, we have 1s2. You can look back to here, 1s2. Then we're going to have the 2s, then we're going to have the 2p6. What does this give us? This says 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if you add this up, you can see that we're already 10 electrons in. We have just 10 more to go. What comes after 2p6? You can look over here. It's going to be 3s2. Then we have 3p6. And then we have not 3d10. No. We have 4s2. And with this 4s2, we have reached our 20 electrons, and this is going to be the full electron configuration for calcium. Now let's do the electron configuration for selenium, which has an atomic number of 34, so it has 34 electrons. So let's start again with 1s2, 2s2, this is 4 electrons in. Then we have 2p6, 10 electrons in. Then we have 3s2, 3p6. Then we have, again, 4s2. We fill up 4s2 first. Remember. Do not forget. This is 20, so we have to keep going. Now we come back to that 3d shell, and we fill it up. So we're going to have 10 more. So we have 30, and we just have 4 more. So what comes after 4s? Again, or 3d in that sense. Look over here. Look at the arrow. 4p. So we're going to have 4p, and then we only need 4 more, so 4p4. And it's going to be our electron configuration for selenium. Alright, so that was it from me for today. It might seem a bit complicated, or your style might still not get it, but do a couple of examples, like think about these orbitals. When I first heard of it, I was a bit confused. This diagram really helped me because I could actually visualize how this was taking place. Do a couple of examples with configuring just to get familiar with, and you realize it's really not that complex, and it's actually pretty cool. Like, imagine electrons filling up these orbitals. Although what must be said is that these orbitals are just probabilities of finding the electron, where there's like a 99% probability that the electron is in here. But nevertheless, we configure them to kind of at least have a rough idea of where it is. So I hope you enjoyed this video, and I hope you have learned something new, and see you next week.